Have you ever wondered why a sunset stops you in your tracks? Why the symmetry of a butterfly's wings captivates you? Or why, across every culture and throughout human history, we find ourselves drawn to certain patterns, proportions, and harmonies? The question of beauty seems, at first glance, to belong strictly to the realm of art and philosophy, subjective, cultural, personal. But what if I told you that beauty isn't just in the eye of the beholder? What if the very laws of physics that govern our universe, from the swirl of galaxies to the dance of subatomic particles, have encoded within them principles that we recognize as beautiful? Picture yourself standing on a beach at sunset. The sky erupts in gradients of orange and purple, reflected perfectly on the water's surface. You feel something, a tightening in your chest, a momentary suspension of thought. Your brain is registering something profound, something that transcends language. But why? Is there something objectively beautiful about that moment? Or is your response merely a subjective quirk of human consciousness? The answer may lie not in poetry or philosophy, but in the fundamental equations that describe our reality. To understand why beauty exists from a physical perspective, we need to journey back to ancient Greece, where the first systematic attempt to quantify beauty began. In the 6th century BCE, Pythagoras discovered that musical notes that sound harmonious together have simple mathematical relationships. A plucked string, when divided exactly in half, produces a note exactly 1 octave higher than the original, a 2-to-1 ratio. Other pleasing intervals correspond to other simple ratios: 3-to-2 for a perfect fifth, 4-to-3 for a perfect fourth. Pythagoras and his followers were so struck by this correlation between mathematical simplicity and beauty that they declared, "All is number." They believed the entire cosmos operated according to these same mathematical principles. Fast forward to the Renaissance, when artists and architects became obsessed with a particular ratio known as the golden ratio, approximately 1.618. Leonardo da Vinci called it the divine proportion and incorporated it into works like the Vitruvian Man. Architects designed buildings and rooms with dimensions that adhered to this ratio. Why? Because something about these proportions pleased the human eye. The Parthenon in Athens, built long before the mathematical formalization of the golden ratio, nevertheless incorporates these proportions throughout its design. But is this just cultural conditioning? Do we find these ratios beautiful because we have been taught to? Or is there something more fundamental at work? Dr. Olivia Young, a theoretical physicist at Cambridge University, has spent her career investigating what she calls the fingerprints of elegance in physical laws. The universe, she explains, consistently favors certain organizational principles: symmetry, efficiency, and economy. And remarkably, these same principles trigger aesthetic responses in the human brain. Consider crystalline structures. Snowflakes form their intricate, six-sided patterns not because they are trying to be beautiful, but because water molecules naturally organize themselves into hexagonal structures as they freeze. The symmetry we admire is a direct consequence of the physical forces at the atomic level. Similarly, the spiral pattern of seeds in a sunflower head follows the Fibonacci sequence, where each number is the sum of the two preceding ones: 1, 1, 2, 3, 5, 8, 13. Creating what mathematicians call the golden angle of approximately 137.5 degrees between successive seeds. This pattern isn't designed for human appreciation. It emerges because it's the most efficient way to pack seeds. Beauty in nature, says Professor Wendy Goldstein, an evolutionary biologist at Cornell University, is often a byproduct of optimization. What we perceive as beautiful frequently aligns with what is mathematically optimal or efficient within physical constraints. But this raises an intriguing question. Why should our brains be wired to find mathematical efficiency and symmetry pleasing? Is there an evolutionary advantage to perceiving beauty in the physical world? Or does our aesthetic sense reflect something deeper, perhaps a recognition of the fundamental patterns that govern reality itself? The plot thickens when we consider that our aesthetic preferences aren't limited to visual patterns. Humans across cultures show remarkable consistency in their appreciation for certain landscapes. Research by evolutionary psychologists suggests we tend to prefer environments resembling the African savannas where our species evolved, open spaces with scattered trees, visible horizons, and bodies of water. These preferences make evolutionary sense. Such environments offered our ancestors both resources and safety. But our aesthetic responses go far beyond practical considerations. When you gaze at a starry sky or stand at the edge of the Grand Canyon, the sense of beauty you experience seems to transcend mere survival value. What's happening in your brain during these moments? Neuroscientist Dr. Omar Yanovsky's groundbreaking research using functional MRI has revealed that when subjects view images rated as beautiful, whether natural landscapes, mathematical equations, or works of art, their brains show activation in the medial orbitofrontal cortex, a region associated with pleasure and reward. Interestingly, this same region activates when mathematicians contemplate what they consider elegant equations. The brain's response to mathematical beauty is indistinguishable from its response to visual or musical beauty, Dr. Yanovsky explains. This suggests beauty isn't just cultural. It's wired into our neural architecture. This neural wiring might explain why certain mathematical constants appear repeatedly in our aesthetic judgments. Take the golden ratio again. Plants don't know about this ratio, yet many grow according to its principles because it represents an optimal solution for growth patterns. Nautilus shells form logarithmic spirals based on this ratio not for aesthetic reasons, but because this growth pattern maintains the shell's shape as it expands. The mystery deepens when we consider physics at its most fundamental level. In 1963, physicist Paul Dirac made a remarkable observation about the equations that successfully described nature. They tended to possess mathematical beauty. It seems that if one is working from the point of view of getting beauty in one's equations, and if one has really a sound insight, one is on a sure line of progress, Dirac wrote. This statement might seem like subjective opinion, except for an uncanny pattern throughout the history of physics. Equations considered mathematically beautiful have consistently proven more likely to accurately describe reality. Consider Einstein's field equations of general relativity. G mu nu equals 8 pi g/c t mu nu. Physicist and Nobel laureate Frank Wilczek described this equation as Mozart's music written in mathematical notation. Its elegant simplicity belies its extraordinary explanatory power, describing how matter and energy curve spacetime, creating what we experience as gravity. But why should the universe care about beauty? Challenges Dr. Young. Why should the fundamental laws governing reality align with human aesthetic preferences? This coincidence is either meaningless, a random alignment between human psychology. This preference extends beyond visual patterns. Soundscapes in nature, from bird songs to rushing water, often exhibit 1/f noise, a specific statistical pattern where the power of the signal is inversely proportional to its frequency. Music across cultures tends to mimic this same statistical pattern. When composer Winifred Godfrey analyzed the statistical properties of Bach's compositions, she discovered they followed the same 1/f distribution found in natural sounds. Our aesthetic preferences aren't arbitrary cultural constructs, Godfrey argues. They're aligned with the statistical properties of the natural world, properties that emerge directly from physical processes. But here's where the mystery deepens into what philosophers call the unreasonable effectiveness of mathematics in describing the physical world. The same mathematical principles that create efficient natural structures, from the hexagonal cells of a beehive to the spiral arms of a galaxy, also produce patterns that trigger pleasure responses in our brains. Consider the phenomenon of wave interference. When two waves interact, they create patterns of constructive and destructive interference, regions where the waves amplify or cancel each other. These interference patterns appear throughout nature, in ripples on water surfaces, in the iridescent colors of butterfly wings, created by light wave interference, and in the quantum wave functions that describe subatomic particles. Remarkably, the same mathematics that describes these physical wave phenomena also describes harmony in music. Musical consonance, combinations of notes that sound pleasing together, occurs when sound waves reinforce each other in patterns of constructive interference. Musical dissonance, combinations that create tension, involves patterns of destructive interference. The physics of wave interference underpins both the shimmer of a butterfly's wing and the harmony of a Mozart sonata, notes acoustics expert Dr. Young. The same mathematical relationships that create physical beauty also create auditory beauty. This correlation extends to the very structure of matter itself. Crystals, from snowflakes to diamonds, form geometric patterns because these arrangements represent minimum energy states. The atoms settle into positions that minimize repulsive forces and maximize attractive ones. What we perceive as the beauty of a snowflake is actually a visual representation of an energy minimization problem solved by physics. But perhaps most intriguing is how these principles extend to the cutting edge of fundamental physics. String theory, a candidate for the unified theory of everything, posits that all particles and forces in the universe are manifestations of tiny vibrating strings. Different vibration patterns create different particles. Remarkably, the mathematics required for string theory includes geometrical structures of extraordinary complexity and elegance called Calabi-Yau manifolds. These structures possess what mathematicians call mirror symmetry, a deep and unexpected relationship between completely different geometric spaces that nonetheless share identical physical properties. This symmetry wasn't invented by physicists. It was discovered as an inherent property of the mathematics that best describes physical reality. The deeper we probe into fundamental physics, explains theoretical physicist Dr. Omar Yates, the more we encounter mathematical structures of astonishing beauty, symmetries and relationships that weren't designed for aesthetic appeal, but emerged naturally from the logical consistency of the mathematics. But this brings us to a profound paradox. Why should human aesthetic judgment align with the mathematical structures underlying physical reality? Is it mere coincidence that what we find beautiful often mirrors the organizational principles of the cosmos? The answer may lie in understanding that beauty isn't something we project onto the universe. It's something our brains evolved to detect in the universe. And they evolved to detect it because recognizing certain patterns and proportions conferred survival advantages. Consider our ancestors living on the African savanna. Those who could quickly distinguish the subtle symmetry of a predator's face from random vegetation patterns had a survival advantage. Those who could recognize the fractal patterns of edible plants among random foliage found more food. Those who could detect the statistical regularities in their environment, the 1/F noise patterns that signal normal conditions versus the unusual patterns that might signal danger, lived longer. Our aesthetic sense isn't some mysterious, transcendent quality separate from our biology, explains evolutionary psychologist Dr. Wendy Grant. It's a highly sophisticated pattern recognition system tuned by millions of years of evolution to detect the mathematical signatures of health, fertility, safety, and sustenance in our environment. This theory gained powerful support from a groundbreaking 2019 study led by computational neuroscientist Dr. Owen Young. His team trained an artificial neural network to perform survival-relevant tasks in simulated natural environments, finding resources, avoiding dangers, and navigating efficiently. They didn't program any aesthetic preferences into the system. Yet after sufficient training, when shown various patterns, landscapes, and mathematical relationships, the AI consistently assigned higher values to stimuli exhibiting the same properties humans find beautiful. Certain proportions, including the golden ratio, fractal dimensions around 1.3 to 1.5, and balanced complexity. The AI independently evolved aesthetic preferences similar to humans. Dr. Young explains, this strongly suggests beauty isn't arbitrary. It's an efficient solution to the problem of quickly identifying valuable patterns in our environment. This evolutionary perspective clarifies why beauty often correlates with truth in science. The patterns our brains evolved to recognize as significant symmetry, simplicity underlying complexity, efficient use of resources, are precisely the patterns that tend to reflect fundamental laws of physics. Our aesthetic sense evolved to detect meaningful patterns in the physical world. Consider symmetry, a cornerstone of both beauty and physics. Symmetrical faces indicate developmental stability and genetic health. Symmetrical patterns in nature often signal the presence of underlying order rather than random processes. It's no coincidence that symmetry principles, from the rotational symmetry of a snowflake to the gauge symmetries of particle physics, reveal fundamental truths about reality. Nobel Prize-winning physicist Chen-Ning Yang demonstrated that symmetry principles determine the form of physical laws. The conservation laws that govern our universe, conservation of energy, momentum, and charge, arise directly from symmetries in the laws of physics. Emmy Noether's revolutionary theorem proved that every symmetry in a physical system corresponds to a conserved quantity. These aren't human inventions but discoveries about the inherent structure of reality. When physicists seek beautiful equations, explains Dr. Young, they're not imposing human aesthetic preferences on nature. They're using beauty as a heuristic, a shortcut to identifying patterns that accurately describe reality. This principle guided Einstein's development of general relativity. When faced with mathematical difficulties, he consistently chose the more elegant solution, not out of arbitrary preference, but because mathematical beauty signaled deeper truth. The resulting theory has withstood over a century of experimental tests with unprecedented accuracy. But the relationship between beauty and physical reality goes deeper still. Recent research in quantum mechanics suggests beauty may be fundamental to the fabric of reality itself. The quantum measurement problem, how quantum systems decide which of many possible states to assume when measured, has led some physicists to propose that reality selects states that maximize a quantity called quantum elegance. According to this hypothesis, when a quantum system has multiple possible configurations, nature favors the one with the greatest mathematical elegance, defined as maximum symmetry and information content with minimum complexity. This isn't mere speculation. It yields testable predictions about quantum behavior that differ from conventional interpretations. If confirmed, notes quantum physicist Dr. Olivia York, this would suggest beauty isn't just something humans perceive in the universe. It's a principle the universe itself follows at its most fundamental level. This perspective transforms how we understand the relationship between mathematics, physics, and beauty. Mathematics isn't just a human invention that happens to describe physics. It may be the language reality itself speaks. And beauty, defined as optimal organization, symmetry, and efficiency, may be the grammar of that language. Consider the phenomenon of emergence, how complex systems develop properties not present in their simpler components. Consciousness emerges from neurons. Market behaviors emerge from individual transactions. Weather patterns emerge from air molecules. In each case, the emergent phenomena follow principles of organization that maximize certain qualities, information processing efficiency, resource distribution, or energy dissipation, within physical constraints. Remarkably, these emergent systems often exhibit the mathematical signatures we associate with beauty: power law distributions, fractal patterns, and golden ratio-like scaling relationships. Beauty emerges because the universe tends toward certain organizational principles when solving physical optimization problems. Beauty isn't arbitrary or subjective, concludes Dr. Young. It's the visual, auditory, or conceptual signature of optimal organization within constraints. We find certain things beautiful because our brains evolved to recognize optimality patterns that signal truth about the physical world. If beauty represents optimal organization within physical constraints, this has profound implications for how we understand everything from art to consciousness. In art, the most enduring works often capture physical principles that our brains are wired to recognize as significant. The perfect compositions of Renaissance paintings reflect the same mathematical relationships found in stable physical systems. The rhythmic patterns in poetry mirror the statistical properties of natural languages and biological rhythms. The harmonic structures in music reflect the mathematics of wave interference and resonance. Great art isn't random cultural invention, argues art theorist Winona Garrison. It's the distillation of pattern recognition principles that have evolutionary significance, principles directly tied to the physics of our world. This perspective helps explain why certain aesthetic principles appear independently across cultures. The golden ratio appears in architecture from ancient Greece to medieval Japan not because of cultural diffusion, but because it represents an optimal solution to certain design challenges within physical constraints. Similarly, musical scales based on simple frequency ratios developed independently in multiple civilizations because they reflect universal properties of acoustic physics. This convergence between aesthetic principles and physical laws extends to our bodies themselves. Research in biomechanics reveals that the movements we perceive as graceful, from dance to athletics, typically represent optimal solutions to physical problems of energy efficiency, balance, and coordination. What we call flow or grace is often the visual signature of physically optimal movement. A beautiful dance movement, explains biomechanist Dr. Omar Yang, is one where the dancer has found the perfect balance point between opposing physical forces, gravity versus muscular tension, momentum versus control. What we perceive as beauty is actually physical optimization made visible. This principle extends to biological evolution. The patterns we find beautiful in living organisms, from the symmetry of a butterfly to the proportions of a cheetah, often represent adaptations that maximize fitness within physical constraints. Natural selection tends to produce organisms that efficiently solve physical problems, and efficient solutions to physical problems tend to exhibit the mathematical properties we recognize as beautiful. Evolution is essentially an optimization algorithm operating within the constraints of physics and chemistry, explains evolutionary biologist Dr. Wendy Gardner. The beauty we perceive in living organisms is the visible signature of that optimization process. But perhaps most profound are the implications for consciousness itself. If our aesthetic sense evolved to detect meaningful patterns in reality, then our subjective experience of beauty represents a moment when our consciousness aligns with the underlying structure of reality. Neuroscientist Dr. Owen Young proposes that what we experience as beauty might be the phenomenological signature of our brain recognizing patterns that accurately model reality. The pleasure we feel when encountering beauty, he suggests, may be our brain's reward system acknowledging a successful prediction about the world's structure. This theory aligns with predictive processing models of consciousness, where the brain continuously generates predictions about incoming sensory data and updates its internal model based on prediction errors. According to this framework, the aesthetic pleasure we experience when viewing a beautiful landscape or understanding an elegant equation represents our brain recognizing a pattern that minimizes prediction errors, a pattern that efficiently captures the structure of reality. Beauty, in this view, is what happens when our internal models successfully map onto external reality, explains cognitive scientist Dr. Wendy Greenfield. The pleasure we feel is essentially our brain's way of saying, yes, that's how things really work. This perspective might explain why scientists and mathematicians often describe moments of discovery in aesthetic terms. When Archimedes had his eureka moment in the bathtub, when Einstein visualized riding alongside a beam of light, when mathematician Andrew Wiles finally proved Fermat's last theorem after years of struggle, each described their breakthrough in terms of beauty or elegance. That aesthetic response wasn't incidental to their discovery, argues philosopher of science Dr. Oliver York. It was the phenomenological signature of having aligned their mental models with the underlying structure of reality. This connection between beauty and truth has implications beyond science. The profound aesthetic experiences people report in meditation, nature immersion, or profound personal insights may represent moments when our consciousness temporarily aligns more perfectly with reality's structure. The experience of beauty, suggests consciousness researcher Dr. Wendy Garfield, may be what happens when the models our brain uses to navigate reality temporarily align with deeper patterns in that reality, patterns that reflect the fundamental physics governing everything. But this raises a profound question. If beauty represents alignment between mind and reality, does this imply something about the nature of reality itself? Is consciousness somehow built into the fabric of the universe? Some theoretical physicists, including Dr. Young, argue that information and complexity, the building blocks of consciousness, may be as fundamental to reality as matter and energy. According to this perspective, what we experience as consciousness may be a highly complex manifestation of the same information processing principles that govern the universe at all scales. The same principles of optimal organization within constraints that produce what we call beauty in physical systems, Dr. Young suggests, may also give rise to what we experience as consciousness. Both beauty and awareness may be emergent properties of information systems reaching certain levels of complexity and integration. This provocative hypothesis remains speculative, but it offers a tantalizing possibility that our subjective experience of beauty may represent moments when our consciousness recognizes its own fundamental nature reflected in the world around us. When we experience beauty, Dr. Young proposes, we may be recognizing patterns that reflect the organizational principles underlying both physical reality and consciousness itself. Beauty may be what happens when the universe recognizes itself. As we stand at the intersection of physics, evolutionary biology, neuroscience, and consciousness studies, a remarkable picture emerges. Beauty isn't just a subjective human construct or an arbitrary cultural invention. It's a window into the fundamental nature of reality, a glimpse of the organizational principles that govern everything from atoms to galaxies, from neural networks to ecosystems. The patterns we find beautiful, the golden spirals of galaxies and seashells, the fractal branching of trees and blood vessels, the symmetries of crystals and equations, aren't beautiful because they conform to arbitrary human preferences. They're beautiful because they represent optimal solutions to physical problems within constraints. And our brains evolved to recognize these patterns because doing so helped our ancestors navigate reality more successfully. When we experience beauty, whether in a sunset, a mathematical proof, or a musical harmony, we're experiencing a moment of alignment between our consciousness and the fundamental organizing principles of the cosmos. That flutter in your chest when you witness something truly beautiful isn't arbitrary. It's your brain recognizing a profound truth about how reality works. This perspective transforms how we understand both physics and human experience. It suggests that the laws of physics aren't just abstract rules that happen to govern reality. They're expressions of organizational principles that maximize certain qualities within constraints. And our subjective experience of beauty isn't separate from these laws. It's our consciousness recognizing and aligning with them. Perhaps this is why beauty feels transcendent, because in those moments, we're experiencing a connection to something that transcends our individual existence. We're recognizing patterns that reflect the very principles that organize the cosmos. The physics behind why beauty exists reveals that we are not passive observers projecting meaning onto a meaningless universe, but conscious participants in a reality structured according to principles our minds evolved to recognize. A reality where truth, beauty, and the fundamental laws of physics are expressions of the same underlying order.